Okay, so hello everyone. In this video, we will cover semaphore. First, we will see that what is semaphore, and then types of semaphore, which is counting semaphore and binary semaphore. And at last, we will discuss a very important question on binary semaphore. In this whole topic, binary semaphore is very important topic. So, moving forward, in GATE and other competitive exams, many questions are asked on semaphore. So, what actually is semaphore? It is a method or tool used to prevent race condition. We have seen race conditions in our previous videos. When we synchronize process or run multiple processes at a time, especially cooperative processes, something is common between them. If so many processes run simultaneously, race condition can occur, leading to data loss, deadlock, and many other problems. To remove or prevent race conditions, one of the method is semaphore. Let's start with the definition. Semaphore is an integer variable which is used in a mutually exclusive manner by various concurrent cooperative processes in order to achieve synchronization. So, what is semaphore? It is an integer variable, and this integer variable is used by multiple processes in mutually exclusive way to achieve synchronization. Now, types of semaphore. There are two types of semaphore. Semaphore are basically of two types: counting semaphore and binary semaphore. The value of integer variable can vary from minus infinity to plus infinity in counting semaphore, but in binary semaphore there are only two values, 0 and 1, as the name suggests. So let's first discuss counting semaphore. Before starting counting semaphore, we use many different operations in synchronization. Where do we use operations? In our critical section. Critical section basically contains common code. Whatever is in the common between multiple processes, we keep that in the common piece of code inside the critical section. When multiple processes try to use critical section, they want to enter critical section, but to enter they have to first run entry code, and when they complete their work in critical section, they have to run exit section code. So this is the fundamental concept. Now, various operations in semaphore, counting semaphore. The operations are P and V. We can also call P is also called as down or wait, and P down, wait, these operations are used in entry code, and V up and signal, these operations are used in exit code. Entry section code, down operation. Let's say initially critical section is free and multiple processes want to enter. To enter critical section, they have to execute entry section code, which is down. Now, down operation is what? S value is equal to S value minus 1. If S value is less than 0, put the process PCB in suspended list. Process control block. What is PCB here? Process control block. So put the process PCB in suspended list, like sleep operations. So S value is equal to S value minus 1. Let me explain with an example here. Let's say semaphore value S is initialized with 3. So process P1 comes, runs down, S value is equal to 3. So then S value is will become what? 3 minus 1. Now S value is 2. So check if S value is less than 0 or not. No, it is 2. It is not less than 0. So P1 successfully entered the critical section. Now process P2 comes, runs down, S value is equal to what? 2 minus 1, because P2 has come now. So 2 minus 1 is equal to 1. Check if S value is less than 0 or not. No, 1 is not less than 0. So P2 successfully enters critical section. Now process P3 comes, it runs down. S value is equal to what? 1 minus 1 equal to 0. Check if S value is less than 0 or not. No, 0 is not less than 0. 0 is equal to 0. So P3 successfully enter the critical section. Now we have three processes, P1, P2, P3 in critical section. Now let's say P4 comes. So P4 will execute this code, runs down, S value is equal to what? 0 minus 1. So it will become minus 1. Check if S value is less than 0 or not. Yes, now S value is less than 0. It is minus 1. Now put P4's PCB, process control block, in suspended list. So we will put P4's PCB in suspended list. Now process P5 came, runs down, S value will become what? Minus 1 minus 1 is equal to minus 2. So check if S value is less than 0. Yes, it is less than 0. So minus 2 is less than 0. Put P5's PCB in suspended list. So P4 and P5 is in the suspended list. If semaphore value is minus 4, it means 4 processes are sitting in the block state. If S value is 0, any further process cannot enter critical section, as they will go to block state. Exit section code. Now we will discuss exit section code. Up operation. We have seen down operation, that how down operation will be performed. Now we will see up operation. When processes in critical section complete their work and want to exit, they run exit section code, which is up. Now what is up operation? S value is equal to S value plus 1. if now there is a condition, if S value is less than equals to 0, select a process from suspended list and wake up. Now this is the up operation. So we will continue with our example where S value was -2. P1, P2, P3 are in the critical section, P4 and P5 are blocked. P1 wants to exit. So what will happen? It will runs up operation. So up operation will be what? S value is equal to -2 plus 1 is equal to -1. So it has executed this code. Now it will check that S value is less than 0 or less than is equal to 0. Yes, it is -1, so it is less than or is equal to 0. So select P4 from suspended list and wake it up, put in the ready queue. Now P2 wants to exit. So P2 wants to exit, run up operation. S value is equal to -1 plus 1 is equal to 0. Check if S value is less than or is equal to 0 or not. Yes, it is 0. So it is equal to 0. So select P5 from suspended list and wake it up. Now P3 wants to exit. It will run up code. So S value is equal to 0 plus 1 is equal to 1. Check if S value is less than 0 or not. No, 1 is not less than 0. So no process to wake up, just increment value. Now we will increment the S value to 1. Wake up doesn't mean putting process in the critical section, it means putting it in the ready queue so it can try again to enter critical section. Now sample question on counting semaphore. Let's say question is at any point of time semaphore value is 10. How many processes can enter critical section carefully? 10 processes. When it goes from 0 to -1, process gets suspended. Now what is question 2? Initial semaphore value is 10. After performing 6p operation and 4v operation sequentially, then what will be the final value? After 6p operation, 10 minus 6 is equal to 4. After 4v operation, 4 plus 4 is equal to 8. This final value will become 8. So our answer is 8. Now what is question 3? S value is 17. Performing 5p, 3v and 1p operation in sequence, what is the final value? Initial is 17. After 5p it will be 17 minus 5 is equal to 12. After 3v it will be 12 plus 3 will be 15, and after 1p it will be 15 minus 1 which is 14. So final value will become 14. Now binary semaphore, we are moving forward to binary semaphore. It is very important. In binary semaphore values can only be 0 or 1. The same synchronization work is done with the just these two values, making it easier to use than counting semaphore, because in counting semaphore we have values -infinity to +infinity. Now operations of binary semaphore. Down operation, if S value is equal to 1, then we will run this code. S value will become 0. Else S value is not is equal to 1, then block the process and place it in the suspended list. Unsuccessful operation. Now what is up operation here? If suspended list is empty, now S value is equal to 1, else select a process from suspended list and wake up. This is the up operation. Now let me explain this with the example of process P1 and P2 both executing. Now assume initial value is equal to 1. So if P2 runs first, P2 executes down S. So S value is equal to 1. Yes. So S value is equal to 0. P2 enters the critical section successfully. If P1 tries to run, P1 execute down S. S value is equal to 1. No. S value is equal to 0 now. So P1 gets blocked. When P2 exits, like P2 executes up S, so suspended list is empty? No. Suspended list is not empty. P1 is there. Wake up P1 from suspended list. This ensure mutual exclusion. Only one process can be in critical section at one time. So this is what? This is binary semaphore. Now we will see a question, then this fundamental concept will be clear to you. There are 10 processes. P1 to P9 executes this code and P10 executes this code. P mutex critical section, then V mutex. This is the code for P1 to P9. Now P1 to P9 process will execute this code. P10 executes this code. V mutex critical section, V mutex. What is the maximum number of processes that may be present in critical section at any point of time? So this is the question, we have to solve it. Let's assume mutex is initialized to 1. P1 executes P mutex, mutex becomes 0, P1 enters critical section. P2 to P9 cannot enter as mutex is equal to 0, so they get blocked. But P10 can enter because it executes V mutex. V mutex becomes the 1. P10 enters, not mutex is equal to 1. So one of P2 to P9 can enter now. Say P2 mutex becomes 0, P2 enters the critical section. At this point we have P1, P10, P2 in critical section. But we can do better. When P10 exits, it executes V mutex. The entry and exit of P10, we can eventually get all processes P1 through P9 into the critical section along with P10. So the maximum answer is here 10 processes. So that's it for this video. We will meet in next video. Until then, bye bye.